This is what happens when you work in places. Sometimes you just get delayed in one place. Okay. So what we have to do today is look at some more graphs. Basically, alright. So some people didn't, or maybe did, take these papers. Somebody is very disappointed. It's the same thing. Alright. So anyone who doesn't have these papers from yesterday? Where are you? Alright, so these are the official papers we started yesterday, and these are extra practice papers that are optional. You may want or not want them, it's up to you. But there are 2 copies on one sheet, so you have to split it up. So one large paper, one smaller one. Just cut it in 2. Cut it in 2, there's enough. There's enough. You have to cut one sheet in 2. Actually, I do need one for myself. I need something for myself. Obviously, although perhaps. So this is from yesterday. This is from yesterday, so those who were here yesterday don't have to take them.
Oh, it's one.
Yes, there's 2 copies on one. I printed 2 copies on one page. So these are to be cut into parts. All right.
No, that's just the question because I know
I will show you a couple of examples today, and the rest of the time actually is up to you for practice. I did email you the first and the second exercise answers. Nice, colorful, computer-made. So today I will just show you the thing about graphing the reciprocal function of any other function and functions that are defined piecewise, meaning piece by piece by piece, interval by interval. After those 2 examples, I think I didn't put them on paper, so I have to copy those F's from my file here, and then I'll send this around so you can sign and see. Some, quite many. And I have to say that towards the end I was becoming more and more angry. But some people still showing up.
No,
right.
They left. And now they're coming.
They left and then they came back. Okay. I'm sorry. I thought I might send you an email when I knew I was going to be late. About half an hour ago. I might have sent you an email, but I wasn't sure that anyone would notice. So I wasn't sure. So if this ever happens again, do you get notifications for email? Normally, do you know when an email comes? So I can send you an email if I have to warn you that I might be 15 minutes late or something.
Normally in the phone.
In the phone or the email, yes. Well, if you have email in your phone, if your phone calls you, I have forced my phone not to tell me when I get emails, because otherwise, some students send me homework at 2 a.m. and it wakes me. And that was the moment when I made my phone not to notify me. Silent. So basically, I spend most of my day in front of the computer, so the phone, I don't need the notifications on phone. But, so, exercise 3, let's talk a little bit about about the two more trigonometric functions, the secant of x and the cosecant of x. So we're going to do the secant of x is 1 divided by cosine of x, and the cosecant, so sometimes you might write cosecant like this, but most computers and most calculators actually, if they ever accept it, they generally write CSCX, which is, guess what? 1 divided by the sine of x. And there's a difference. Now, many computers and calculators use the notification sine inverse of x. This notation means arc sine, the inverse of sine. This means inverse. This means arc sine of x. So make sure you understand the difference, because this sort of exponent minus 1, it's not really an exponent minus 1. It's the sign of the symbol for the inverse function. So it's not this. This is not this. This is something different. This is the inverse function, and this is the reciprocal of the sine function. So this is the inverse of sine, and this is the reciprocal of sine. Reciprocal of the sine function. So the reciprocal of a number is, as you know probably, the number 1 divided by this, or actually by definition, strictly speaking, the reciprocal of any number is such a number that the product of those two equals 1. So the reciprocal means 1 divided by whatever you want the reciprocal of. Inverse function, we discussed this yesterday. So these are two different things. This notation refers to arc sine, to the inverse of sine. If you see this in your calculator, and you do, on many calculators they use this notation, and many of you are actually used to this notation, perhaps in your own school where you come from. This means inverse. This does not mean the reciprocal. So you have to be very careful with all functions, because in functions, when we look at functions, this symbol, exponent minus 1, it means inverse. It never means this. So if you want to discuss the reciprocal function of whatever function, you have to write it like this, so that there is no doubt and no misunderstanding at all. And so how do we graph reciprocal functions for functions whose graphs we know? Suppose we know the graph of a function f of x. So how do we graph the function 1 over f of x, the reciprocal of this function? How can we do it? It's obviously there are no shifts, no stretches, there's something else, there's something completely different. This is something completely different from what we have been doing, for example, yesterday. So what happens here? What happens here is, let's have a look, some logical reasoning. For example, if the given function equals 1 at some point, then the reciprocal function, obviously, also equals 1. So actually all the points that are at level 1 on the y-axis stay where they are. If the function equals 0, then the reciprocal function obviously is not defined there. 1 divided by 0, impossible. So the function is not defined, and basically this function might be infinitely large or infinitely, well, large, a negative infinitely large value. So there might be a vertical asymptote at that point. On the other hand, if this function is infinitely large, for example, if it has a vertical asymptote, then this will become equal to 0. So there are some interesting things. And of course, if you know some values for this function, then you can deduce the corresponding values of the reciprocal function. And so let's consider the function, for example, cosecant. For example, the cosecant. So we need the sine function, we need the sine graph to start with. Okay, so this is 1 minus 1 on the y-axis. And on the x-axis we have pi half, pi, 3 pi halves, 2 pi, minus pi, minus 2 pi. Let's remember, if x equals pi half sine value, the sine value is 1. If 0 or pi, then 0. If 3 pi over 2, then it's minus 1, then 1 again, and we have to get used to the shape of the sine graph. Okay, and here we have minus 1. Right. Here we have positive. Something like this. So we have the graph of the sine function, and now let's use this to figure out what the graph of the cosecant function of this one should look like. So this is the function y equals sine x. Now let's try to figure out what the cosecant should look like. Obviously, if the sine function equals 0, 1 divided by sine, 1 divided by 0 does not exist. So we have this vertical asymptote here. This, so we can sketch in vertical lines, because at these points, 1 divided by 0, we will have, well, roughly speaking, infinity. So this is all done by logic. Obviously, if the given function is positive, then the reciprocal function will also be positive. If this is negative, then the reciprocal function will also be negative. Those things are not so difficult to decide. So if the given function, the sine function, equals 1, then the cosecant function will also be equal 1 at that point. So this point, actually, and this point, and well, somewhere, this point belongs to the graph of the cosecant. If the given function is negative, minus 1, then the reciprocal function is also minus 1. So these points actually belong to the graph of the cosecant. Now what next? We might think sometimes the sine value is 1/2. At those points, the cosecant value will be what? 2. Right. So I can say, okay, so if this is 1/2 here, then at this point, obviously, the cosecant function will be 2. We don't need too many of those points. Just a few to figure out the shape of the cosecant. And of course, we can see that the same happens here. At this point, the sine function is, the sine value is 2, so the cosecant value at this point will be is 1/2, so the cosecant value at this point will be 2. The same goes for the negative values. So if the sine function is negative, so -1/2 at these points, then the corresponding cosecant value will be -2. The reciprocal number, the reciprocal value. So I'm sketching this simply to indicate the same level, the same height. All right, so we can already see, and of course, if the original function is decreasing, then the reciprocal function is correspondingly increasing, and so on. Then if the sine value approaches 0, then this value becomes very, very large. If it approaches 0, the sine function, the original function, approaches 0, being positive, then obviously the reciprocal function becomes very, very large and positive. So it tends to infinity. Here as well, the sine value approaches 0, the reciprocal tends to infinity, and it's positive, so the reciprocal is also positive. So we should do this. And of course, at pi, where the sine function is 0, this reciprocal function is not defined. So we have this asymptote, this vertical line being approached. And here the same happens if sine value, the given function, approaches 0, but being negative. Then obviously the reciprocal function becomes very, very large, but also negative. So a large absolute value, but the function itself negative. And the same happens here. So one period. After that, everything repeats itself. So you can imagine that the next part of this cosecant graph is there. The next part of the cosecant graph will be there. The next part of the cosecant graph will be there, between these two vertical lines, and so on and so on. So you see the cosecant function in red now. This is the graph of the cosecant function. And this is basically how we deal with all reciprocal functions that we need. For instance, in number 4, y equals x squared and y equals 1 over x squared. How you might get the reciprocal function of the quadratic function, for instance. There are other possibilities, other things, but basically my aim is to show you how you might get the graphs of some functions, or at least the approximate graphs of some functions which are unfamiliar to you sometimes. Sometimes you might see an unfamiliar function and you simply deduce the shape of that graph from the given function, from the original function. For example, in a similar way, you can sketch 1 over x squared. You can sketch 1 divided by square root of x, for example. If you know the basic graphs, you can sketch the reciprocal functions. Using the same considerations. So if the original function is 1, and you can see it from the graph, you don't have to do anything with the formula. You simply sketch the original function, and then you concentrate all your attention to the graph. You don't need the formula anymore. So you think, okay, points x1, something 1 stays where they are. Points something minus 1 stay where they are. If a function approaches 0 being positive, that means the reciprocal function shoots up. If it approaches 0 being negative, then it goes down along the asymptote. Some specific values, for example, you might want to draw the horizontal line or sketch in very lightly a horizontal line at 1/2, y equals 1/2, meaning that at these points the reciprocal graph will become, the value will become equal to 2, 1 divided by 1/2. If the original function is, for example, equal to 2, then the reciprocal function will become 1/2. In this function, if you have x squared equal to 4, that means the reciprocal function will be 1/4. So you can sketch some extra points to help yourselves, but basically the considerations that there are some points that remain where they are, some static points, or points that don't move at all. Then there are some points that simply transform into asymptotes. The zeros transform into asymptotes. Asymptotes transform into zeros, and so on and so on. So basically it's based on logic. There are no strict rules in what order or what exactly you should do. So probably the points where the y value is 1 and -1 are useful because they simply remain where they are. Some special values geometrically might be found, and then the dealing with zeros, wherever you see a 0, you draw a vertical asymptote, and then you think whether the graph will be going down to infinity or up to infinity, more or less. So I will leave the secant function for you to do by yourselves. I will also leave number 4, x squared and 1 over x squared again to do by yourselves. Right now I would like to have a look at number 5. These piecewise defined functions. What does that mean? It means that the function has a different formula for each segment of the y-axis. For each part of the y-axis, the function, the graph consists of several pieces. These pieces might be joined at some point. The function might be continuous, or there might be some gaps between these pieces. Let's have a look at, well, which one would you like?
I'm sorry, where's the attendance list?
I told you, I will let you start your work, and then I will write. I haven't written your fails in the attendance list. If you want the attendance list, just so I can give it to you, no problem. You can wait some minutes. Okay. Nobody wants to see that. No, well, actually there are a couple of times. But then there are a lot of fails, and then there are a lot of letters C.
What is
Cheating.
Cheating. There are no 6 or...
No, well, there are 6. There might be, for example, something like 5C or 4C, which means those people don't get a second chance for now. They have to keep that one. So if I notice that somebody has cheated, I mark what I can up to that place. As soon as I see that cheating place, I stop looking at that question at that point. So you might get partial points as long as you do things correctly in some question. As soon as I see a mistake, I stop.
One more little question.
Yes.
How many exercises does somebody have to do in a test to get the minimum?
It depends. It depends, because I saw that this test was.
For example, last test.
Because well, this last test, I did what they call it in the States, curve the grades, which means I didn't use plain percentage, which normally, for example, 45% is the absolute minimum for a 4, normally. In this one, I lowered my standards because I saw that this test was indeed difficult for all of you. So you don't have to look at those percent, because first of all I looked at those actual scores. I looked at what you should or what you would or might get, and then I looked at the overall situation. Basically, to get a 4, you have to understand something. So there were a lot of people who still obviously didn't understand anything, or not enough. Normally, in a normal test, it's 45%. And to get, so the upper boundary, no, in a normal test, not in this one, the upper boundary of 8 is 85%.
Yeah, 8.5.
So that's the top of 8 normally. Normally that's the top boundary of 8. So the top 15%, the top 15% are split between 9 and 10. Generally something like 9% here and 6% here. Sometimes it's 8 and 7, or actually equally. It depends on the test. But because I saw that this test was difficult, I was, let's say, trying to be gentle, but towards the end it didn't make much difference.
So 10 is not means everything is okay?
No, not necessarily. No, you don't have to do 100% to get the 10. You might still afford to lose, for example, some 5%, lose 5%, and you may still get 10, no problem.
It's like rounding, you can from 9.5 to 10.
That's something.
Yeah.
That's something. But this was I had to use non-standard grading simply because I really saw that this test was difficult. So those who got 10s or 8s might feel, let's say, very satisfied with themselves, because those are well deserved, and those correspond to the actual whatever, almost the actual whatever there is. And and the rest of you will basically it's more or less one grade up, more or less approximately. Yes, except those C's, they make me angry. C's make me angry. There's no problem. And by the way, yes, I'm not a detective. I'm not a detective. I don't care who is the author and who is the copier. So if I see two equal, identical mistakes in two papers, I put C there and there. I don't care who's the author. It's not my duty to investigate. So, I have to teach you somehow.
So basically, if you cheat, you fail automatically. Or do
if you cheat, you still might pass. Depends on how good you are at whatever you do.
at copying, yes.
You know, there are so many people who copy without actually understanding what they are copying.
Yeah.
I have seen people who look at a square root, but in somebody's handwriting it looks like a 5. So instead of this, they write 5x. What other proof you need?
Okay.
But I've seen it, or somebody writes U and somebody else sees it as a 4. It happens, and it's very easy. Well, sorry, I'm probably too old. I've been teaching for too long. Because I can't help seeing it.
Have someone copied me? Have someone copied me?
No. Not the name, but still, it's obviously students will be students. I can't help that. That's probably something that will never ever end. But I try. And another thing is you have to see that I do see things. It's not that I don't even have to look at you really. I take your papers and I can say things. Okay. Yes, you're waiting. Okay, but you were asking questions. Okay. Let's have a look at 5. Which one? 5b, 5c?
5C.
5c. All right. So let's look at 5c. 5c, the function f of x is defined as follows. It is equal to 2x minus 5 for x greater than 3. It is equal to x squared minus 1 over x plus 1 for x between 3 included and 0 excluded. And the square root of minus x for x less than or equal to 0. Okay, this is an interesting one, especially the central part, the middle part. So what we generally do is, of course, I sketch the system of coordinates, and I see that there are 2 points that actually separate this x-axis into 3 segments, 0 and 3. So this 1, 2, 3, 3. So actually I can see that if I split the whole plane, the whole system of coordinates into 3 parts, I will have one part, one graph, one kind of graph. In this part, another kind of graph. In this part, and another kind of graph in this part. So for each of these parts, I have to sketch a separate graph and then choose the correct part of this graph, and the correct piece of this graph. All right. 2x minus 5 for x values greater than 3. So obviously I need to find at least one point. For example, if x equals 3, then that function would be 1, equal to 1. So, alright, I mark an empty point here, and this is actually sort of moving partly into the new topic, into the next topic, because on Thursday we are going to begin limits. And this moves slowly, even this reciprocal function graphing and this part, we are moving slowly into understanding limits. And so if we use this function, for x equal to 3, the value of this function is 1. Unfortunately, x is not equal to 3. So I sketch in an empty point. I mark the point that it's empty. It doesn't belong to this part. Now, 2x minus 5 means the gradient, the slope is 2, which means 1, 2, 1, 2, 1, 2, using the gradient. So I can actually sketch the line, or actually the half line that corresponds to this particular part of the graph. So for x values greater than 3, the graph of the function is the same as for y equals to x minus 5. So unfortunately this point has to be cut out, an empty point, a hole if you like, but this is the first part, so this is this part. And I'll probably use colored pens to indicate, yes?
Can you just repeat one more time? So whenever you have
the empty point I have, because you see, if x equals 3, then this formula should work.
Okay.
If x equals 3, then we see that this formula is applied. So x is greater than 3 but not equal to 3 for this one. But I need the point simply to be able to sketch the graph. I can use that point. I could actually use even the point x equal to 0 when it would intersect the y-axis at minus 5 and do 1, 2, 1, 2, 1, 2, this thing. But I would still only use this half of that line. I can use other points in other parts. The thing is that in the end, I have to choose the correct part of that graph. Sometimes I need to use, let's say, a piece of parabola. So I might sketch the whole parabola, for example, and then say, okay, this parabola applies only in this segment between 0 and 3, so I ignore the other parts. I will mark it stronger, or with a colored pen, or just discard or erase those other parts, the unnecessary parts. So you can sketch the whole graph. Simply don't forget to discard the unnecessary bits. All right. If x is between 0 and 3, now that function looks a little bit nasty. Perhaps we can change it a little bit. X squared minus 1 divided by x plus 1. 7th grade algebra. X squared minus 1. X plus 1, x minus 1. So we can actually simplify this. But with one exception. X cannot be x cannot be minus 1. We see x is not equal to minus 1. It will be, so we can see it will be a straight line, x minus 1. Again, the graph is a straight line, but it will be a line with a hole.
But it's not necessary because it's from 0 to 3.
From 0 to 3, oh yes, right. It's not equal to minus 1, right. I was thinking about 1. So at this point we would have a hole. So all right. So x minus 1 means minus 1, 1. So the part of, so and this would be 2. This is at 2. I would have this. Now x equals 3. This function does work. So this is the full point. Now we can see that when x equals 3, the value of the function is 2, but not 1, the full point, because 3 is included there, 0 is excluded there. So we can see that these two parts of the graph of this function have a gap. There's a jump. Actually, that's what we call it, jump discontinuity, but we'll discuss it next time or perhaps next week. So this gap has a special name, a jump discontinuity. And by the way, as I said, if I had to graph the full line, if I had to graph the full line, then it would mean that for x is minus 1, we would have a hole in that line. If I had to use this part, I would see the hole in that line because x cannot be equal to minus 1. Fortunately, we don't need it. But if, then it would be a hole because this very clearly shows us that x cannot be equal to minus 1. Minus 1 does not belong to the domain of this function. But in general it does because we can use this part. So the second part is done. It's this. Now square root of minus x. We know what the square root of x looks like, don't we? Half of a parabola, remember? The square root of x. So the square root of minus x works only if x is negative. F of minus x means that the graph actually has to be flipped over the y-axis, facing left, going this way. So that's what I'm going to sketch now. The square root of minus x, in other words, half of parabola, but facing backwards. And equality. So this is the full point now. Now you see this graph of the piecewise defined function, piece by piece. Actually, the three parts are not connected between themselves. So that might happen sometimes. That's not a big tragedy. Sometimes simply different processes are going on. For example, if you heat, for instance, water or start with ice, perhaps, or you heat water and the temperature rises and then the temperature stops rising because it reaches the boiling point. And then when everything has boiled, if the volume is contained, then the temperature starts rising again, but now this is for the steam. So you might see that the same process sometimes, well, because of the differences of the physical processes in the nature, these functions might just happen. Another situation where these functions might happen, for example, in architecture or engineering, where you have to model some structure, it's not necessarily the same function all through the situation. So it might be that there's one function showing one part of the bridge, perhaps, and then there's another function, perhaps a flat part, and then some other function again to model whatever the other end of the bridge depends. So there might be different functions used depending on the situation. So it's not a pure invention by mathematicians. So sometimes these things simply happen, and we will need these to investigate limits a little bit. For example, as x approaches 0 from the left, the function value tends towards 0. If x approaches 0 from the right, the function value tends towards, what was it? 0 minus 1. So actually there are two different one-sided limits. I'm already stepping a little bit into Thursday's lecture. So the left-hand limit, the left-hand side limit from the left is, as x approaches 0, the limit of the function, the value of the function tends towards 0. The right-hand side limit, as x approaches 0 from the right, the function value tends towards minus 1. And this explains the gap. All right. Now, you should try doing the secant function, the function 1 over x squared, and perhaps The 5a and 5b functions, slightly perhaps more complicated because, no, they are not more complicated. I think this one is more complex than these. You have this paper, so you can actually work. I will work too. And if you have questions or if you get stuck, please come and ask. And I will give you the attendance paper. Of course, some people are impatiently waiting for attendance. Because they want to sign and leave. But of course, I understand very well. There are some people who only want to sign so that they don't appear as missing the lecture, but they don't care for the lecture. Generally, those are the same people that tend to fail. Experience.
There are even more extreme versions of that. People signing for others.
Of course, I cannot force people to work, but I strongly advise trying to do something by yourselves, because I think in my 30 years of teaching, I've had one student who sat like this through all the lessons. He was very good anyway. He could do all the tests almost perfectly. Everybody else who do this in all lectures or lessons could do better. That's just advice. I'm not forcing anyone. But basically, I will not be ready to do any retesting for the vector test before the holidays, I think. The holidays, I mean the 18th of November.
Yeah.
After that, because basically I need to set up completely different problems. I need to, for all those people who seemingly cannot work independently, I have to invent new problems. For those who like to use Wolfram Alpha or something else, I need to invent some statements of problems such that they have to think by themselves instead of just plugging the numbers into Wolfram Alpha, and so on. You know, I'm mean, I'm evil. I'm really, really mean. Okay, now work. Now work. You got your dressing down, now work.